And it says here that you need to know some proton and C13 IR for carboxylic acid and derivative. You want to make sure that we kind of take a minute here and maybe review some of the different functionalities. So if I have an acid, how can I tell the acid from an ester versus, let's say, an amide? And we'll look at the IR first, and that's like 3200, 3600, and that's going to be what? OH. But down here, you have peaks at 1100 and 1300, which is the COC, single bond stretch for the ester. The amide, if it's like this one, right? So primary with the NH2, you get what? Two peaks that are sharp between 3200, 3600. Now if you had a secondary where you had an alkyl group attached to this nitrogen, then you would have only one peak in that region. But again, it's sharper than the OH. How about if I'm looking at the proton NMR? Here, 12 to 15 ppm is what? It's the H of the acid. So I'm going to put C-OH, and I'm underlining the H because that's what it's coming from. Over here, if it's an ester, realize you can have a peak shifted to 4 ppm because of the ester. And amides are kind of probably the most difficult to analyze because of the fact that the protons on the amide actually exchange with the solvent system. Okay, so that kind of, and just to kind of go back over, the C double bond to O's in all of these, you know, C13 will probably show up around the same area. The only thing we add to this is, remember the iodoform test, which is the test for methyl ketone. Ooh, here's one of our multi-step synthesis reactions. And what we have here is benzene ring with a nitro group. But the big thing is we have an ester. So you got to remember esters, since it's an acid derivative, you want to go back to the acid chloride. And the acid chloride goes back to carboxylic acid. But realize carboxylic acid is a meta-directed. Meta position would be right here. And what we have is a nitro group in the para position. So that has to come back from the toluene derivative in a way, and then now we can remove the nitro group to get back to toluene, which goes back to benzene. Forward direction. To put a CH3 group on, this is Friedel-Crafts alkylation, which is we use CH3Cl in the presence of a Lewis acid catalyst like AlCl3. And that puts the CH3 group on the ring and makes toluene. Then when we nitrate the ring, we get nitro group probably in the ortho position too, but we're going to say that, you know, part of the product will be that p-nitrotoluene. We treat it with KMNO4 OH- in heat. That will oxidize the CH3 to the carboxylate anion. Then we have to put in H3O+ so we can protonate our acid. Reaction of the acid with SOCl2 gives us our acid chloride. And then lastly, using CH3OH, we get our final product. Okay, so let's go back to our review sheet. Now it says to review substituent effects on acidity. Now there's two things we want to look at here. The first thing is the fact that we have either what's called an inductive effect, which is going on the top here. This is what we see here. If I put a halogen on the alpha carbon, that's going to have an electron withdrawing effect on our carboxylic acid. And as the pKa of our acid goes down, that means our acid strength is going up. So therefore, when we get to trichloroacetic acid, we see that this is a very strong acid as opposed to acetic acid, which is a weak acid. Now the other way we can look at this is looking at a variety of benzoic acid derivatives here. And if we have an electron donating group, then we can have a resonance donate into the ring where this would actually decrease the acidity of our control, which is the benzoic acid. But when we put nitro groups on, depends where that nitro group is. If the nitro group is in the meta position, we only get inductive effect, no resonance effect. But if we put the nitro group in the para position or the ortho position, we're going to get a resonance effect. Now you notice here the ortho position has a stronger effect than the para, and that is primarily because the O- on this nitro group partially probably has an effect on getting this proton removed from the acid, okay? And we'll capture that. So what we're saying here is if I drew this, and I draw my acid up here, remember the nitro group is here, And one of the oxygens on the nitrogen group, remember, is negatively charged. The nitrogen group has a positive on the nitrogen, negative on the oxygen. So this could actually have an effect in here, pulling that H off. And that's why you see the increase. How can we purify or separate, let's say, an acid from an alcohol? Remember, acids are soluble in base, so we treat with sodium hydroxide, and this forms that sodium salt of the carboxylic acid. And the ether layer is our alcohol. So now that they're separate, we can just add H3O plus an ether and have our carboxylic acid. Again, I'm just going to do a quick capture so you have it. And now I'm going back to our review. Okay. We don't have to worry about these diacids here because that was on the last test. What you want to know, though, is the names of some of these things that are going on here. And what we see here is over here, we are getting rid of CO2 up here, and that is a decarboxylation. We're going from this beta keto acid to the ketone, and that's decarboxylation. Here is 2 moles of ethyl acetate going to our ethyl acetoacetate. The name of that reaction is called a Claisen condensation instead of an aldol condensation. Here we have a special reaction here. We're going to have a Michael addition, right, followed by an aldol condensation. We call this Robinson annulation. You notice we go from a single ring to 2 rings. That Michael reaction is where groups, like these dialkyl lithium cuprates, can add to the beta carbon, and you get the CH3 over here. Because this is what we call a soft nucleophile, it will attack you get a 1,4 addition instead of 1,2. Now, last one here, special reduction using lithium triterbutoxyaluminum hydride. Notice, only one H available to deliver for the reduction. You get the H delivered to the C of the C double bond O, and you end up with an aldehyde. Okay. Here is another multi-step. Again, we have an ester. Ester, since it's an acid derivative, right, is going to come from the acid chloride from the acid. Okay, now we notice we have from benzene, this is kind of like, we can look at this as 2 carbons, or we can look at it as 1 more carbon. If it's 1 more carbon, right, we can go back to benzyl bromide, which goes back to toluene, toluene back to benzene. So to put a CH3 group on, we have CH3Cl, AlCl3, NBS. Why is the Br here? Because it's allergic to a double bond in the ring. We take that halide and react it with magnesium and ether. That gives us our Grignard. CO2, right, followed by H3O plus gives us our carboxylic acid. Then again, react with SOCl2 to give the acid chloride, and methanol to give our final product.